Welcome to your fourth webinar. In this webinar, we are going to have a walkthrough to your first project, and I will share with you some useful tips for finishing this project successfully. And there's not going to be any solution, and it's just going to be some helps for you in order to write each of the to-dos. So that being said, let's get started. In this project, you will build a hidden Markov model for solving the problem of parts of speech tagging, which you will give in a sentence and you will be asked to give a tag or label to each of the words in this label. And you will use a pomegranate library for making a hidden Markov model. This Jupyter Notebook is divided into 4 parts. The first part is read and processing the dataset, which you will go through your dataset. You will know the actual structure of it, and you will get familiar with some of the method in it. The second part is to build the most frequent class tagger, which you will have a dictionary of the words mapped to the most frequent tag. We will go through each of these more thoroughly. And the third part is to build a HMM tagger, which at the start you will write for count function, unigram count, bigram count, starting count, and ending count. These are very similar to each other, so if you can write one of them, it's very easy to write the other one. And lastly, you will also write the emission probability and transition probability, and you will be totally done with this project. However, there's a fourth part, which is optional. In this part, you will given a larger text set or larger labels, and you'll also given some tips for improving the model. If you're interested, you can actually pursue this as well. So let's back to our Jupyter Notebook and start with reading and processing our dataset. Let's start by importing 2 libraries. Firstly, we will import NumPy, and secondly, we will import helper, which has been already provided for you, this will help us for loading our dataset. Okay. Now let's load the dataset. Let's say dataset is equal to dataset that we have already imported. And let's take a look at the arguments. At start, you see a tag file, which it should be in the same directory with the name of tags universal. And there's a data file. This is also in the same directory with the name of brown universal text. And also, thirdly, we have a train test split, which we want to have 80% training set and 20% test set. Okay. So now let's take a look at our dataset. This might take a while because the dataset is massive. And if you wait a little bit, you will see that the structure is similar to this, which at the start we have sentences with some ID. Each sentence has its own ID, and also in the same dictionary you can find the words that we have, words in a sentence. It also has tags, corresponding tags. For example, Mr. is equal to the tag of noun. Podger is equal to, okay, this is the data set is loaded, and Podger is equal to noun. And if you look, there is a lot of these ideas and sentences which we will now go through each of them, how to actually take each of it. So let's start by checking the how many sentences we actually have. We both in our whole data set and also on our training and test set. So let's say number of sentences in the whole data set. So the dataset that we already loaded, we can say like just sentences. It will bring all of the sentences in our dataset. So there is around 57,000 sentences in our whole dataset. We can also access to the sentences in our training set. Say number of sentences in the training set, which first we say data set, then we just say training set, and we will access to our training set. And for getting the sentences, we will again say dot sentences. So in our training set, we have around 45,000 sentences. Now lastly, let's take a look at number of sentences in our test set. Which same as above. Instead of training set, we will say testing set and also sentences. So now we have 11,000 for our test set. Now let's check the unique vocabularies that are in each of these whole dataset, training set, and also test set. So let's see. Number of unique vocabularies in the whole dataset. Which instead of sentences for getting the unique vocabulary, we say vocab. Data set. And in our whole data set, we have 56,000 unique vocabularies. We can do the same thing for our training set. Number of unique vocabularies in the training set, which same as above. At the start we will say training set, then we will say vocab, which we have 50,000, around 50,000 unique vocabularies in our training set. And lastly, let's do the same thing for our test set. So we just say dataset dot testing set vocab. We will take the length of it, which is around 25,000 unique vocabularies. So now let's take a look at our tag set or the labels that our dataset have. For let's say labels, let's take a look at our labels. Which for getting the unique labels, we just say tag set, data set, the tag set. And this is the whole label that you're going to work, like noun, adjective, and so on. There, in general, there's 12 labels. You can just print it out as well. Total number of labels. Which is 12. Okay, now as you could see, we have here unique IDs for each of the sentences. If you have the IDs, you can actually get the sentences and also its tag sets. let's say that we want to take the whole sentences. You would say just dataset sentences as before, and we just put our ID inside the empty bracket. Oh, we already have this, and we can get our sentences, which is the words and the tags itself. You can also get just tags or just words. You can do this simply. We will do the same thing. Each dataset dot sentences. We will get our unique ID, words and tags, and at the end we will just say words. And here we got a tuple of just words. We can do the same thing also for our tags. Each dataset, sentences, get our unique ID, and we will say tags. And here just the tags. So now we can actually also get the words and tags in another way as well. For getting the training set, we can say .x, dataset.x, or for getting the labels, we can say .y. So let's see. Let's say we want to show the words in the first sentences. You can say x, which it will get the words, y is tags, and get the first one. This is the same thing as above, but in here we don't use any ID, and we want to just say the first sentences, and you can get the first tags as well by just saying .y. This will bring all of the tags. And if you want to get the first sentence, we can say put it in a 0 bracket. There is also another way of getting these words and tags, which we will use something like .stream. This is used only for if you have a loop. So let's take a look at it. Which we are going to have a word and corresponding tag set. Dataset .stream. So let's print the word. Also print the corresponding tag. And also give some space in between it so we can have a better idea how it works. Also, let's say if it reaches to 5, let's just break the loop. Okay, as you can see, we can also get the same thing with .stream, which it will loop to the whole data set. It will get the words and the corresponding tags. Okay, now let's go to the second part of this Jupyter Notebook, which you will build the most frequent class tagger. If you actually take a look at this Jupyter Notebook that I shared with you, I wrote down all of the to-dos, like in the second part of your project, and below each of it I wrote down all of the tips that it can help you tremendously if you need any help for solving those problems. And also, for example, if you want to apply the per count, for example, if you have these inputs, you will get something like this. This is not exactly, it might be like the orders might be a little bit different, but the general format should be like this. And now I will go to actual your project Jupyter Notebook, and I will talk about it, but you do not need to listen very carefully because I wrote down all of it in here. Okay, let's go to the your project Jupyter Notebook, and let's go to the second part and let's take a look at it. If you see in here, you're going to have three to-dos. First, you have to write a per count function, and secondly, you have to make an MFC table. And also you have to, of course, apply your pair counts to your tags and words. Let's start with the pair counts. In pair counts, you're going to have two sequences, which obviously is going to be your tags and your words. And what you want to do is to have some format like this, which is going to be a dictionary. Each of the keys going to be your unique tags. As we saw, there's 12, and in each of it there's going to be words with the number of occurrence of it. So the way we approach this is we can first create a dictionary inside of your function, so later on you can append all of the results into it. Then secondly, you can actually iterate through all of your sequence of tags, and also while you looping over, make sure you have enumerate so you can actually know your exact index, because after inside your first loop you will get the equivalent word in a sequence of words using the index that you already created. Then you will check to see if there is any tag inside the dictionary that you have already initialized, and if there wasn't any, then you will make another empty dictionary, and if there was, you will just get that dictionary's tag. And then you will check to see if the word we are in that iteration is inside that the second dictionary or not. If there was, we just add 1 to it. If there wasn't, then we will make it equal to 1. Then we will apply our pair counts to our tags and words, and the way we will get our tags and words is to iterate through all of the tags, and we will append each of the item in an empty list. We should just have one list. Inside that it should be all of the tags, and we'll do the same thing for words. A list that each of the item is words, and we will get this through iterating through it. Then we will put it inside your pair count, and you will get your emission counts. Later on, since you already apply your pair counts to your words and tags, now you wanna make a most frequent count table. So what we wanna have, this is a dictionary that we are going to have, and we want to output something like this, which is a dictionary. Keys are each words, and the values are the most frequent tag that has been already used in it. So the way we do this, we will at the start we will initialize the MFC table to be equal to an empty dictionary. Then we will iterate through the pair counts that you already made to the items in it. We'll iterate through it, and we will consider the words in each of the loop as a key to MFC table. And since there are multiple tags for each of the words, then what we want to do is to get the tag that has the maximum number and assign the value to key. So we will get the word as key, and since there are multiple tags for each of the words, we only will get those that have the maximum number. and at the end we are going to have MFC table. And in here we are going to have a very simple model just for detecting, and you will get your accuracy, which is actually going to be very high, which in fact is going to be more than 95% accuracy rate on your training set. So let's go to the third part of this Jupyter Notebook, and in here you want to, at the very start, you will build the unigram counts, then bigram counts, then starting counts, then ending counts. And you will also do your emission probability and transition probabilities, which in general is just 6 to-dos you have to do. So let's start by unicounts. Unigram counts is same as the word count that you have already worked on in your lessons. And what we want to get in here is to actually iterate through each of the sequences and actually count it. For example, if we have something like this, we want to go to each of it and count it. For example, noun is this much, verb is this much, and we want to get something like this. And the way we will solve this problem is to actually, at the very start, we will initialize an empty dictionary, and then we will iterate through each of the item in our sequences, and inside the loop we will check to see if that item is inside the dictionary or not, the dictionary that at the start we initialize it. If the item was inside that dictionary, then we will add 1 to it, add 1 to its value. If there wasn't any, then we will make it equal to 1. And then we will just apply this unigram count to our tags, and in here you can just use data stream. You will iterate through data stream and just get the tags inside one list, and you will solve the whole unigram count. Now let's go to the bigram counts, which is same as the unigram count, but with this difference that we have a tuple or sequence of 2 items instead of just 1. And it is essentially the same thing as here with just very small changes. But before that, let's just see the inputs and outputs in it. The inputs, like same as before, we want to have a list of our tags, and in our output we will have a tuple of 2 items and its count. So we will solve this problem like before by first initializing an empty dictionary for saving all of the results into it. Then we want to get the bigram of all of these sequences. We can do this using NLTK library, which is a very simple one-line code for getting all of the bigrams in this sequence. After getting the bigrams, we will iterate through those bigrams, and inside the loop we will check to see if the item in the sequence is inside the dictionary or not. If there wasn't, we will make it equal to 1, and if there was, we will add 1 to it. If there wasn't, we will make it equal to 1, and we will apply this bigram functions like same as before to our tags. And the way we will get our tags is to iterate through data.stream and get each of the tags inside the list, and we can successfully finish this. Now let's go to the starting count. What does it mean, a starting count? It means that we want to go through our sequences and get only the first tag at each iteration. In ending tags, we want to get only the end tag in each of the sequences, which is the sentences. So let's start by, like same as the other counts, we will start by initializing an empty we will start by empty list, not dictionary. Then we will iterate through each of the sequences and we only append the first tag in each loop to our list. So we have all of the starting tags. Then we will initialize an empty dictionary. And like before, we will iterate through the list that we already got, which is our starting tags. And inside the loop you will see that if the item is inside the dictionary or not. If the item was inside the dictionary, then we will add 1 to it. If there wasn't, then we will make it equal to 1. This exact same process is for ending count, but at the very start, instead of when we will iterate through sequences, we will append only the last item in a sequence or that sentence that we are already in that loop. That's the only difference between starting count and ending count. Then we will apply this starting count to our tags, and which let's take a look at it. This is going to be the inputs, which is going to be tuple of tuple. Each item is a sentence of tags, and the output will look something like this, which we count each of the tags just for starting counts. And for the ending counts, it's same thing, but just the end counts. Now we are all done with our counts, and we can start by creating our emission probabilities and our transition probabilities. Let's start by creating our emission probability distribution, which is this part. In here, what we want to do at the very start, we will initialize an empty dictionary so we can save all of the states inside that dictionary, because later on we're going to use this. After initializing that empty dictionary, we will iterate through each of the unique tags, which in general is just 12 tags. And inside the loop, you will initialize another dictionary, which you will capture emission probability for that specific tag that you're inside that loop. Then you will have your second loop, which you will iterate through your pair counts, and you will get your words and their occurrences in the pair counts. Inside your second loop, you will divide the occurrence, which you got it, to the tag unigram of the tag, and save it to the empty dictionary that you got it in from your first loop. After this, you will get out of your second loop and you will get the discrete distribution of your probabilities, which you will use pomegranate for that. It's a very simple one-line code. Then you will add the distribution to a state. Again, you will use pomegranate for this. And this state, you will add it to the state dictionary that you would initialize at the very start. And then you will add the state to a model. And that's the whole thing is inside the loop. So you're going to have two loops. The first loop you will iterate through your unique tags. Second loop you will iterate through your pair counts. And now let's go to the transition probabilities, which again we will do this inside loop. And we can divide this into two parts, adding the start and end edges, And second part, add in between edges, which is going to be two different loop in general. For adding the start and end edges, again you will iterate through your unique tags, which are just 12. You will get the state for a specific tag, which from the same state dictionary that you got from your emission probabilities. You will get that state for the tag you're inside the loop. Then you will calculate the start tag probabilities. And the way you do this is to divide that specific tag in tag start, which you did this before, to the whole sum of the values in that tag start. Then you will add that start probabilities in between states in your model, which again you will use Pomegranate for it. Which now so far you added all of the start edges. Now you can inside your loop, you will, for adding the end edges, you will calculate the end tag probabilities, which you can calculate it by dividing that specific tag in the tag ends that you created before to the whole sum of all other values in the tag ends. Then you will add that probabilities to your model using Pomegranate. So far you added the start and end edges for your transition probabilities. Then what you want to do is to actually add in between edges. And again, you will iterate through your unique tags, your 12 tags. You will get the state for that specific tag from the state dictionary that you got from your emission probability. Then you will initialize a variable, for example, let's say sum of probabilities to 0. And you will have your second loop now, which you will iterate through your unique tags for the second time. Inside your second loop, you will again get the state for the specific tag from your second loop, and you will get the diagram of two tags, which the only thing you have to do is just have a tuple, and the first item in the tuple should be the first tag from first loop. The second item in your tuple should be second tag from your second loop. Then you will calculate the transition probabilities. Then you will add that transition probability to sum of probabilities that you initialized with 0. Then you will add the transition probabilities to our model using Pomegranate. And with the basic model.bake, you will finalize the whole thing. And that is it. With this, you can finish the whole project. In here, you can check the accuracy, which this is necessary. You get the accuracy more than 97% for your training set and more than 95% for your testing set. And in here you can actually predict the sentence and you will see it. And you can finish the project by converting it to HTML. And you're totally done. That's how easy it was. And this is the optional part for if you're interested to use the HMM model for larger tag sets, which is going to be more than 12 tags that you're going to work with. And for sure, when you larger the tags, the accuracy is going to be a little bit lower. So there is some tips for you in here. You can higher the accuracy. And that is all. I hope this could help you in any way to solve your problems. Thank you very much.